Hi, my name is Tony Mason, and this is my Milestone 3 report for CS6460. A brief synopsis of my project is that I decided to investigate interactive training for operating systems. My observation was that operating systems education is an important element for success in computer science study, and in previous work I provided evidence to back that up. In addition, I noted from both my personal experience as well as a number of data sources, including from the OMSCS program, that operating systems courses have a high dropout rate. Some of the reason for this is the material is complicated, the presentation is challenging, the workloads are very high. There are a number of different reasons. I specifically am trying to address the material and the presentation of the material, the goal being to provide a more interactive experience to the student so that they can become more engaged in the material and hopefully gain better retention and become less likely to drop out. I used a tool called Opia, which is an open source training delivery system, in order to build this interactive training. I specifically decided, based upon the time that was available for the project, to focus on 4 critical areas in operating systems. That included processes, threads, scheduling, and synchronization. Thus, I am developing material on all 4 of these topics. This is milestone number 3 of 4. Since milestone number 2, the synchronization exploration has been released on the Opia site, and the older explorations regarding processes and threads have also been updated. The next milestone, which is the final milestone of the project, will release the scheduling exploration and then review and revise all of the existing material, as well as provide a final project report. I previously have stated these concerns, but I thought I'd briefly capture them here again for anyone who has not seen the previous work. I have a certain level of dissatisfaction with Opia. It is not nearly as robust and interactive tool as I had been hoping. I did spend some time investigating alternatives, but decided that there is insufficient time to change direction at this point in the project. Still, it's educational in looking forward on how to approach this in the future. I have received more feedback. One of the concerns I had on the last milestone report was I had not received much feedback. I have now received more feedback, including an extensive editorial review of the process module that I just received late last night and have not had an opportunity to process yet. So, in order to better show you what I have been doing, I have I am preparing this video to walk through and discuss in greater detail the synchronization exploration. The term exploration is how Opia describes things. Now, before I get too far into this, I do want to show you what it looks like on the back end when I'm actually building these things. So Opia does provide me with this graphic layout showing me how the content and material actually flows. And one of the things that I have done differently in the synchronization module than I did previously, based upon feedback, is I've tried to make things a little more linear. The previous exploration on threads, I was told, is a little confusing because there's a fear that you're going to miss material. So this time I was more careful to make sure that as you walk through the paths, it's very easy to go back and look at things you might have missed, or to move through things that you don't really want to know more about. There's quite a lot of material actually in this section. And the approach that I took here certainly could do with further expansion and refinement. But I think it's a very good, solid beginning. So let's go back and look at the actual exploration. So we have a brief intro slide. And I decided to leave a brief intro slide in here because Opia actually makes it difficult to insert anything at the beginning otherwise. So I learned that the hard way. I had to redo an entire exploration as a result of it. And thus I got into the habit of leaving a small place marker at the beginning. So the first thing I want to do is make sure that students have actually gone through previous explorations. If they say no, what will happen is they will be taken to a page that says, gee, you probably should go take processes or threads. Alright, so that doesn't work so well. Start all over again. So this time I'll say yes, I have. So let's get started. So we talk about processes. We talk about address spaces. These are concepts that we've used previously. And then we talk about threads, and then we finally start moving into the topic at hand, which is synchronization. How do we coordinate between them? I've tried to incorporate a number of graphic elements this time. I used some last time. I've used a number this time as well. I would absolutely love to put even more diagrams in and figures in here, but unfortunately it's very time consuming to develop those, and again, this is one of these balancing acts, trying to make sure that the material that is there is solid, even though it doesn't have as many graphical elements as I'd like. This is actually an analogy that I routinely use when I teach synchronization using my existing materials, and that is I talk about intersections and how intersections are similar to the way that threads interact. So the way that cars share intersections, the way that threads share data structures. And of course, if you do it wrong, bad things happen. The goal here again is to try and engage the student, to make them understand things, and to blend between abstract concepts and concrete examples. Now, this is an analogy, so it's not a concrete example of exactly what synchronization is, but it shows a good general paradigm that should be familiar to people, so that it will make it easier for them to understand what we're talking about. So now we have our intersection, and we talk about the need for synchronization. I point out that you don't always need to synchronize things. Anything that doesn't have scope to other threads doesn't require synchronization. So let's start talking about how operating systems provide synchronization. Then we talk about mutual exclusion. I continue to try and balance between a discussion of both Linux and Windows, because those are the two predominant operating systems that people will experience in everyday life. I suppose we could certainly continue talking about OS X as well, but OS X and Linux are sufficiently similar that it doesn't bring enough additional variety. So we introduced the idea of atomic operations, because those are critical to our conversation about mutexes, mutual exclusion. And then we provide an example of when we might perform a particular operation. In this case, we're looking, is the queue empty? If it's not empty, take something off the queue. And of course, we have two distinct steps here, and the possibility of the state of the queue changing between these two. Now, I'm not using real code here. This is a pseudocode. It might be better to actually pick a particular code, but we'll see what kind of feedback I get from people. I think that's pretty clear what's happening. So we continue to move through it. So now here is one of these branching points where you can say, do you want to learn more about atomic operations? And if we go back and look at the diagram here, you can see, so we're here, hardware atomicity, and then we have a whole discussion about atomic operations going into some pretty deep detail. There's actually a video presentation in there about the MESI protocol, which is the classic cache coherency protocol that's in use on Intel machines these days. MESI stands for Modified Exclusive Shared or Invalid. But let's say we don't want to do that because we are already familiar with that. Maybe we've taken the computer architecture class, so we understand all about cache coherency protocols. So now we're going to say, great, so how do we actually build a mutual exclusion, a mutex, from these atomic primitives? And I give a classic example. This is actually an example of the way that Windows does it. And then we can look at the Linux implementation if you want, or maybe you already know or you don't care. So Linux actually implements it in pretty much the same way. The fundamental primitive there, the mutual exclusion of the operating system, is the spin lock, and I have a link off to the Linux source code, so you can actually open up another page for the Linux source code, and then I talk about the Linux concept of a futex, which is a kind of mutex. It's not as heavyweight as a spin lock, and it's used to build most of the higher level synchronization primitives. So we can go back, or we can go forward to synchronization issues. So here we were in mutexes, so we can now go forward to synchronization. So we're skipping all the way down here, or the other approach, the other model would have been to go to mutual exclusion, which is where the previous card was supposed to go if you didn't go down the Linux mutex path. So let's see, maybe we can go back. Nope. All you can actually see are the cards that you've gone through. You can't change your path through them. So we can talk about race conditions, deadlock, and slow performance. Let's just pick one. Let's get back to synchronization. So as you can see, I've picked in a number of places. I've picked existing videos and put those existing videos in there. I've tried to pick a variety of different videos. When we talk about programming concepts, they are from different languages, because fundamentally, while the operating system itself is probably going to be written in C, the users of these abstractions, the application programs, are going to be written in a broad range of languages. And there's nothing magic about C, that it's really the concepts here that are what matter. So now we talk about a problem around reference counting, and we can go into greater detail about that, or we can talk about lock-free operation. If I go back over to, so here you can see one of these slides, it's actually set up to autoplay, so you can hear it. You can hear it playing. So this is now synchronization, slow performance, deadlocks, race conditions. All of these things flow around in between each other, or eventually lead to more synchronization, which is where I went. And then I went down reference counting. That's going to lead into the ABA problem. Lock-free operations. Let's see. So this is the ABA problem. Might as well just actually walk through it. Lock-free operation. I'm giving people the opportunity to skip out there. Here's a nice picture. I really liked this. This is an example of, once again, our car analogy with a roadway that eliminates the need to actually have mutual exclusions here, because everything is set up so that it doesn't require traffic lights, our equivalent of a mutex. So talk a little bit about issues here, deadlock performance. So this is lock-free programming, and we just talk a little bit about lock-free programming, what reference counting is. We can go back over here. I can show you that branch here is down here. So what we did was, right, lock free programming, and then that will take us down to the summary. Or we can go back. So that will bring us to the summary, and that brings us to the end. I don't have a forward reference here, but I will probably add a forward reference to the scheduling exploration, because that would be the next logical exploration to go on, to follow this. In all fairness, you could probably go to both scheduling, or either scheduling or synchronization in parallel, because there's not as much overlap between them. Processes to threads makes a lot of sense. Threads then really is a fundamental requirement for a discussion of either scheduling or of discussing synchronization. And that is basically the current state of the exploration. I want to thank you for sitting through this presentation, and as a thanks to those of you who have to actually review it, if you'll send me your email address, I will send you an e-gift card. So for the first person to do so, I'll make it $25, and then $20 for the second, $15 for the third, and $10 for the fourth person. If you're after the fourth person, then, well, sorry. But I do appreciate all of your feedback, and I appreciate the fact that you sat through this